Okay, so I'd like to invite our second speaker in this session. So second speaker is going to be Johan.
Yep.
Yeah. And she's going to talk about posterior sampling-based privacy enhancing large language models. Because today's session is around LLM.
So hello everyone, my name is Yulian, and today I would like to share our ongoing research. Our short paper is PSY, Posterior Sampling Based Privacy Enhancer in Large Language Models. This is a collaborated paper with Huawei Unique Research Center, Bochum University, and the University of Paderborn. Okay, let's start to talk about large language models. Here is the image from the survey paper, a survey from large language models published in December 2023. It shows the timeline of existing large language models. The authors of this survey mark the large language models with publicly available model checkpoints in color yellow. We can see how the landscape of large language models has expanded. Besides the direct usage of large language models for asking questions or translation, if people also want to use large language models for other particular tasks, then we need fine-tuning. So the most popular fine-tuning method is LoRa. You can see the image. It will replace LoRa, the popular fine-tuning method, which stands for low rank adapter. And the image shows the workflow. It replaces the change of weights with a product of two ranks. For example, if we say a pre-trained model W0, it will replace the then the updated weights will be a W0 plus the product of B and A. So if we do the fine-tuning, after fine-tuning, large language models may memorize information. So the adversary can extract the input data in inference. We find existing solutions for reducing memorization. The first is from Ren et al. They identify and remove highly memorized samples. The second one from Sampali et al. Their method aims to prevent the generation of sensitive samples. The third paper is from Hindersdorf et al. And their method is to localize and remove memorization neurons. So they all modify something in the data sets or models. So we think about other alternatives. Instead of removing, can we add tiny modules in large language models that can effectively hinder memorization? So the answer is yes. And variation autoencoder, the VAE, is a tiny module we need. Why? Variation autoencoder, the VAE can give a privacy guarantee. This has been proved in our paper, exploiting internal randomness for privacy in vertical federated learning, which has presented at the main conference in Zurich this year. So if you have your interest, you can read our paper. So what is VAE? I will introduce it. So the image shows the architecture of VAE. How does VAE works? Intuitively, an input X is randomly mapped to a sample from distribution by VAE. The distribution is Gaussian-like with mean of mu learned by X and noise with weighted Gaussian sigma of X multiply epsilon. The exact form of mapping is determined by the training process, the training data sets, the random epsilon, and the X itself. Actually, we only need the part of AE, the posterior sampling part, the yellow rectangle part. So how do we insert the posterior sampling part in LoRa? The right image shows the structure of LoRa with posterior sampling. So let's go back with LoRa. When we have a pre-trained model, W0, the updated weights, W0 plus delta equals W0 plus BA. Then if we insert the posterior sampling between A and B, for input X, the latent output C is mu of AX plus epsilon times sigma of AX. So for example, if we fine-tune a hidden layer edge, the final output equals W0 times X plus B times C. And we evaluate our method based on functionality and defensive ability perspectives. We set up two kinds of privacy attacks: data extraction attack, which a black box setting. The adversary has no access to the trained model and has no prior knowledge. And the membership inference attack is also a black box setting, and the adversary has no access to the trained model, and it can only query the trained model. We choose 3 large language models: GPT-Neo, Red Pajama, and Pisces. And 3 data sets: AG News, Twitter, and Wikitext. So let's look at the experiments in data extraction attack. We choose 3 metrics: perplexity, lower casing, and zipping. Perplexity measures the fine-tuned model in their word predictions. Lower casing alerts the perplexity of memorized content, which requires a specific lower case. And zipping alerts the memorized content, which has repeated texts. So in comparison with baseline, which has no privacy protections, and the differential privacy with parameter epsilon equals 0.1, the results show that our method can reduce memorization. Then look at the results of member inference attack. So the attack performance, according to their true positive rates under very low false positive rates, and we choose 3 different threshold values: 10%, 1%, and 0.1%. Compared with the baseline, also has no privacy protections, and with differential privacy with parameter epsilon equals 0.1, our method shows that it can defend against membership inference attack. However, some weird results in Red Pajama and the Pisces, when use DP, when the threshold is 1% and 0.1%, there are zeros. In conclusion, we proposed an efficient module, PSY, to mitigate memorized related attacks. In the future, we would like to investigate our other LoRa-based fine-tuning methods. For example, co-LoRa. Besides, we plan to quantify the privacy guarantees of PSY further and explore alternative modules that can have similar effects. That's as references. Thank you.
Okay, thank you very much for the presentation. This open for the presentation for the questions. Anyone have any questions? Okay, so a quick question actually from me. Can you go back to your slides? I think at the very beginning. Yeah, go down to the next one. You mentioned that micro methods, the existing methods.
Okay.
Yeah, actually, so these are the existing methods.
Yeah.
Yeah. So so how do you identify and remove highly memorized samples? So what do you mean by highly memorized?
They are choosing when they do the fine tuning. They actually do some tasks as they
So there's
This is my second
research. There are alternatives of each of the neuron can be highly memorized. Right?
Yeah.
So the straightforward way, which has not been optimized, is directly, well, let's prompt that neuron and see the results. It's one of the basics methodology they have used. They have a lot of optimizations of choosing that out. And then they make a score for this highly memory neurons.
Okay, so they identify the highly memorized neurons.
And then just prompt them or give them some level ways to read in fact.
Okay. Okay, it's basically using Buddhist techniques to remove those.
Yeah. Reset and find and remove.
Okay. Any other questions? Okay, let's thanks for the speaker then.